Okay, so we've talked about the method of substitution, and that opened up a whole bunch of functions that we can integrate, functions involving compositions of functions. We want to attack a few more of the so-called transcendental functions. So what are transcendental functions? Well, the transcendental functions are opposed to what we call algebraic functions. So algebraic functions are polynomials, basically any function that's obtained by doing the standard operations of addition, subtraction, multiplication, division, doing exponents in roots and radicals and things like that. So you've got polynomial functions, rational functions, and those sort of things. Transcendental functions then are functions that are not created by that, and so that's going to include some we already know, like the trigonometric functions: sine, cosine, tangent, secant, cosecant, cotangent, and those. We know some of those antiderivatives already, but not all of them. We know sine and cosine's antiderivative, and from the substitution method, right, I showed you how to find the integral of tangent, and hopefully you found the integral of cotangent. We still have cosecant and secant to worry about, but we'll do that later. But there are other transcendental functions, and we're going to look at some. And the first we're going to look at are the inverse trig functions. So those are kind of sometimes students kind of forget kind of the behavior of those. They're a little bit challenging in some ways, but I want you to recall that. Here is the, first of all, inverse sine function. Remember this little exponent here is not an exponent. This is not sine of x to the negative 1 power. So be real careful of that. This is not sine of x to the negative 1 power, right? Because what is sine of x to the negative 1 power? That is 1 divided by sine of x, which is cosecant x. That's not at all what we're talking about. This is the arc sine function. This is the sine inverse function. So the only time we interpret this as an exponent is if it's a positive integer. So it's a challenging notation, but the superscript -1 often implies an inverse. Think of f inverse, right? The inverse function. That's the notation we use. Okay, some of you are familiar with arc sine function because of the unit circle and how the angle, the central angle, is equal to that arc length, provided we're in radians, and that's where this arc sine comes from. Here's the graph of it. Notice the domain is -1 to 1, which matches the range of the sine function, if you remember the relationship between inverse functions. And the range is -pi/2 to pi/2. And of course, that doesn't quite match the domain of sine. If you remember, the domain of sine is all real numbers. The problem with the sine function, right, on its domain is all real numbers, but it's going up and down, right, between 1 and -1, if you remember the graph of the sine function, right? And the problem is it's not 1 to 1, so we can't define an inverse on its entire domain. We have to restrict its domain on an interval where it's 1 to 1. And in other words, for every input to the sine function, we want to just have one output. Okay. Sorry. for every input, we want to have a unique output. And so in order to do that, we restrict the interval. And the interval we choose is this interval, mainly because it contains 0. So here's the graph of the inverse sine function. Similarly, we have the inverse tangent function, or arctangent. Now, here's its graph. Its domain is all real numbers, and that's because the range of the tangent function, if you remember, is all real numbers, right? It has vertical asymptotes. The tangent function does. The range, though, of the inverse tangent function is -pi/2 or pi/2, and in fact, because we have vertical asymptotes for the tangent function, we have horizontal asymptotes for the inverse tangent function. If you remember, the graphs of inverse functions are related to the original functions by what? They are reflections about the line y = x. And so it makes sense that the tangent function has vertical asymptotes, the inverse tangent has horizontal asymptotes. And these occur at what? Y = pi/2, which is about 1.57, and down here at y = -pi/2. negative 1.57. And those are important when we're talking about limiting behavior. The limit as x goes to infinity of the inverse tangent function is what? Pi halves, because it's approaching pi halves. As we go to negative infinity, we're approaching negative pi halves. And then here is the inverse secant function. This is one way of defining the inverse secant function. In fact, there's other ways you can define these inverse functions. It gets a little tricky. This one is not as familiar to us. I just show it to you. You can see the strange domain. Basically everything except values between negative 1 and 1. All right, so in between negative 1 and 1, there's no value of the function, and that's because if you think about the inverse or the secant function itself, its range is all real numbers that are greater than or equal to 1 or less than or equal to negative 1. They match this domain. And you can see the strange range as well. Again, this can be slightly different depending on how you define the inverse. But these are kind of strange functions, but again, we're interested in finding the antiderivative, okay? And here's the thing, I hope you remember the derivative possibly of the inverse sine function and the inverse tangent function. Okay, those are ones that are fairly important. Okay, I'm also going to give you the derivative of the inverse secant function. You may not remember that one. But because we know the derivatives, we're going to know the antiderivatives. Or we're going to have a formula for an antiderivative, excuse me. Let me be clarified that. So the derivative of the inverse sine function, or the arc sine function, same thing, is 1 divided by the square root of 1 minus x squared. Okay, so we learned that in Calculus 1. That means, therefore, that the integral of the derivative, the integral rather of 1 over the square root of 1 minus x squared is arc sine x plus a constant, or sine inverse x plus a constant. Right? Doesn't, get used to both notations. We'll see both. Okay, mean the same thing. And then similar here, the derivative of the inverse tangent function is 1 divided by x squared plus 1, and so the antiderivative of 1 over x squared plus 1 again is the inverse tangent function. Again, or arc tangent x. And then finally, the derivative of the secant inverse function with the secant inverse function defined this way, this is the derivative of the arc secant function. Okay, and you got this ugly absolute value down here. It's just a little bit bothersome. You can define the inverse secant function a little bit differently, and the derivative comes out a little differently. But here again, this is the inverse secant function. Okay, the two I want to mainly focus on are these two. By the way, there are 3 more that we haven't mentioned: the inverse cosine, inverse cotangent, inverse cosecant. Inverse cosine is actually the derivative of the inverse cosine is just negative 1 times this, and so you could interpret this integral as being equal to negative arc cosine x. That is actually true. And it kind of makes sense when you think about the derivative of sine and cosine, that the inverse sine, inverse cosine kind of have this plus minus relationship as well, right? But again, if we have a choice between arc sine x and negative arc cosine x, we would prefer arc sine of x just because it doesn't have the negative sign in front of it. And so we'll focus on that. I'm not going to worry about the inverse cotangent or inverse cosecant function, really. The textbook does show you the derivatives for those and the corresponding integrals we get from those, I believe. But it is sufficient to just focus on these two, I think, for our intents and purposes, and that's what I'm going to do. Okay, so that's a little overview. You might need to go back and review a little bit more about the inverse trig functions and how these derivatives were obtained from Calculus 1. But now that we know these, we do need to know these forms here, the first two, for Calc 2. Okay, let's look at some examples then. We'll start off with a definite integral. And here is the definite integral. And so, again, we can see from the forms that we're going to be focusing on that this one is the one involving arc sine of x. So the antiderivative of this is, I'll use the inverse sine notation, and right, that's the antiderivative, and we're going to evaluate that at 1 and at a half, and we're going to subtract. So I expect you to be able to find the exact value of the inverse sine at these values. So I evaluate it at 1 and I evaluate it at a half. So what is the sine inverse of 1? Well, remember the relationship that we have is that if x, let's say if a is equal to sine of b, then sine of a is equal to b, right? We've got that inverse relationship. Now there are some restrictions here, right? Again, because the input to b is any real number here, we can define this, but when we talk about the inverse sine function, right, its range, oh, I'm sorry, this is sine inverse, excuse me. the range of the inverse sine function was negative pi over 2 to 2, and notice that's what's coming out here. The b is coming out of the inverse sine function, so notice the range of the inverse sine function has to match the domain of the function, sine function. And so, you know, again, b can be any real number, but in this relationship here, we would be talking about what b being in this interval. Okay, so if I plug in b to the sine function and get a, well, the sine inverse of a is equal to b. So if I want to find out the sine inverse of 1, right, is equal to b, I want to find sine of what equals 1, sine of what value equals 1, and it has to be a value in this interval, right, from negative pi over 2 to pi over 2. So sine of what value is equal to pi is equal to 1. Almost gave it away. Answer pi over 2, right? Because why? Sine of pi over 2 is equal to 1, and pi over 2 is in this range. Now there's lots of other values where sine is equal to 1, like sine of 5 pi over 2 if I add 2 pi to this, right? But 5 pi over 2 is not in this range. Sine inverse of a half. Well, sine of what is equal to 1 half? Sine of what is equal to 1 half? Answer pi over 6. Again, you can use the unit circle to work through that. Of course, you're going to be looking for what? The sine is the y-coordinate. When the y-coordinate is 1, where are you at? You're at the top of that unit circle, right? At the point 0, 1. That's at pi over 2, right? So that's why we get this. At 1 half, right, the angle is pi over 6. Okay, so you need to be able to find these exact values. And once we do so, we have our answer, right? Pi over 2 minus pi over 6. If I want to combine this as 1, I put them over the common denominator of 6. So pi over 2 is 3 pi over 6. And I get 2 pi over 6, which of course simplifies down to pi over 3. Okay. So make sure you are able to find the exact value of the inverse sine, inverse tangent, and using the unit circle to do that. Let's look at number 2 here. So this is interesting. Clearly, this relates to the arctangent integral here, but it's got tangent inverse on the top. So what in the world? I mean, this is not the same integral as what I have over here. What am I going to do here? You know, this tangent inverse of x, I just can't get rid of it. It's part of the integral, right? It's got a variable assigned to it. Well, think about a u substitution here. Think about a u substitution, and in particular, go back to the derivative, really, of the inverse tangent function. So what I'm going to see if this makes sense, I'm going to let u be the inverse tangent function. Now, when we do our substitution, we typically do what? Choose the composition. We look at a composition, we choose the inner function, right? There's no, that's not, tangent inverse is not inside anything. It's being divided by x squared plus 1. If anything, we would usually choose u to be x squared plus 1 in the denominator, so that we get what, 1 over u, hopefully. But the derivative of x squared plus 1 is 2x, right? The derivative of x squared plus 1 is 2x, not tangent inverse of x. That's not going to work. But if I do choose u to be tangent inverse of x, what is my du? What's the derivative of the tangent inverse function? What's the derivative of the tangent inverse function? Right? So it is 1 over x squared plus 1, or dx over x squared plus 1. So du dx is 1 over x squared plus 1. Multiply both sides by dx. And there it is. Look at that. That's what I have left. Dx over x squared plus 1 is my du. And this integral with that simply becomes the integral of tangent inverse of x, which is u, times dx over x squared plus 1, which is just du. It's just u du. It's just the antiderivative of u. What's the antiderivative of u? That's just by the power rule, 1/2 u squared plus a constant. Go back to the original variable. U is tangent inverse of x, so this is 1/2 tangent inverse squared plus c. Okay. Now, don't do this. Don't multiply that -1 by 2. Remember, this is not an exponent. That is not an exponent. It stands the inverse tangent function. If you don't like the inverse tangent, I mean, you can use this arctangent as well. These are both the same thing. Okay. And again, you can check by taking the derivative. Of course, you need to remember these derivatives and the corresponding integral forms that we're coming up with. Okay, so there's an example of substitution. It's a little different. So as we proceed, sometimes the substitution will be a little different than what we started. 95 probably % of the time, we're choosing the inner function, and then we're going to integrate. Let's go ahead and do one more here. And this is the one I want to look at here. Integral of 2t divided by 9t to the 4th plus 1. Okay, so let's take a look at it. We're dealing with these two integral forms. These are the two we're focusing on. The one that evaluates as arcsine, and one that evaluates as arctangent. Okay, of these two, okay, obviously we got t and not x, but of these two, which one is this probably going to be? Is it going to be this one involving arcsine, or is it going to be this one involving arctangent? Well, since I don't see a square root, then it's going to be involving this. But it's not x squared plus 1, it's 9t to the 4th plus 1, right? So we're going to do a little substitution here. So notice the substitution is going to be a little different. That's going to allow us to get this integral to be simpler, to look like this. In fact, that's one of the uses of substitution, is to get the integral that's complicated to be simpler, to be something we recognize. Something we recognize, hey, I know what the antiderivative of that is. And in order for that to work, what does this have to be right here? This right here has got to be, I'm going to call it u squared. I mean, you can call it x squared if you want. You can use substitution x, but I'm calling it u squared. So du over u squared plus 1 is going to be tangent inverse of u. So that's what I'm hoping the form will become. That's what I think it looks like. Let's see. So if I let u squared be 9t to the 4th. Now this is real important. What is the value of u? If u squared is 9t to the 4th, u is what? Well, think about, what is this being squared? If this is u squared, what's being squared here? How do you get 9? What do you square to get 9? 3. What do you square to get t to the 4th? Remember, you multiply exponents, so that's t squared. 2 times 2 is 4. We're not adding exponents here, remember, we're multiplying. So u is 3t squared. That's what we need to choose for our substitution. So notice there's no, I mean, there is a little bit of a composition if you think about it, 3t squared inside of the squaring function, but it's not quite the same thing that we had been doing previously with the substitution method. But we still do the same thing. We take the derivative. What's the derivative of 3t squared? Bring the 2 down, and I get 6t. Subtract 1 from 2, I get 1, 6t. And then, so du dt is 6t, so du is 6t dt. And now I look at my integral. Hey, look up top. There it is. I got a 2t dt. Here's a 6t dt. So what do I need to fix things? I need to multiply both sides by 1/3. 1/3 du. 1/3 times 6 is 2t dt. And so what does my integral then become? I have the integral. The 2t dt is what? 1/3 du. 1/3 is a constant multiple. Pull that 1/3 out. And I have du over what? 9t to the fourth. What's 9t to the fourth? That's u squared. Plus what? Plus 1. Now, does this now look like one of these integrals that we know? Yeah, it's dead on for this one, right? So that's what we're saying. Get it to look exactly like the one we want. So I know this antiderivative. I have this 1/3, but this is what? The inverse tangent function plus c, right? Of course, instead of x, I've got u as my variable, but same form. And so now I can answer the question by replacing u with what? 3t squared. So here is the antiderivative, 1/3 tangent inverse of 3t squared plus c. Okay. So that's a little introduction. We're going to do a lot more because these are a little tricky. There's some things that we want to be able to think about already, a little bit different type of substitution than what we were used to doing. And so again, we will be doing this sort of substitution a little bit more here, and we'll do that in the next video.